August 27, 2016. A room at NASA's Jet Propulsion Laboratory falls completely silent. They are listening to a spacecraft. It left Earth 5 years earlier. It traveled 1.7 billion miles through empty space, alone, and the data begins to arrive. A scientist named Scott Bolton is looking at readings that should not exist. The core, the solid, ancient core that every textbook for the last half-century had described with confidence, is not quite there at all. Bolton would later describe what Juno found on that first pass as, simply, a surprise. That word, coming from a man who had spent decades preparing for this mission, was doing a great deal of work. Jupiter had been waiting. It just needed someone to come and ask the right questions. Juno launched on August 5, 2011, from Cape Canaveral, Florida. It was a 4-ton spacecraft, and it looked unusual for something headed to Jupiter. Getting to Jupiter is not a straight line. Juno crossed the orbit of Mars and then looped back using Earth's own gravity as a slingshot in a maneuver called a gravity assist. In October 2013, it returned to Earth, not to land, but to borrow momentum. Earth gave Juno an additional boost of more than 16,000 miles per hour. Then the spacecraft was gone again, aimed outward, climbing away from the inner solar system for good. It arrived at Jupiter on July 4th, 2016. The approach was tense. To enter orbit, Juno had to fire its main engine for exactly 35 minutes at exactly the right moment. Too soon, and it would miss. Too late, and it would overshoot, and the science mission would end before it began. Because of the distance, radio signals took 48 minutes to travel between Juno and Earth. There was no way to intervene in real time. The spacecraft had to do it alone. It did. The engine burned within 1 second of its predicted timing. And the team at JPL, watching a telemetry stream of numbers rather than any kind of video, allowed themselves to breathe. Juno was in orbit around Jupiter. But there was a problem. And here is where the story takes its first unexpected turn. The original flight plan called for Juno to complete 2 long 53-day orbits, then fire its engine again to shrink those orbits down to 14 days for the rest of the mission. Tighter orbits, more passes, more data. That was the plan. Then the team inspected the engine. Some valves were not behaving as expected. A misfire during the orbit-shortening burn could be catastrophic. After careful evaluation, the team made the decision to leave Juno in the longer orbits indefinitely. Every flyby of Jupiter would still give the instruments the same 2-hour window to collect data. But instead of every 2 weeks, those windows would come every 7 weeks. The mission would take much longer than planned, and it would discover far more than anyone anticipated. From the very first data collection pass on August 27th, 2016, Jupiter revealed itself to be more complex than scientists had predicted. Let's start at the top. The clouds visible from Earth and from orbit are not simply decorative. They are the surface expression of an atmosphere in violent motion. Juno's instruments showed that the alternating bands of color circling the planet, the dark orange belts, and the lighter zones are actually vast rivers of wind flowing east and west in opposite directions, colliding and interacting with tremendous energy. Before Juno, one of the most fundamental questions about Jupiter was simply, how deep do those winds go? Scientists had debated this for decades. The answer, revealed by Juno's measurements of the planet's gravity field, was striking. The jet streams extend approximately 1,900 miles below the cloud tops. That is deeper than anyone had believed. 1,900 miles of atmosphere in motion, all the way down to where the internal structure of the planet begins to change. Now, the clouds themselves. In the cold upper atmosphere, water, ice, and ammonia interact in a way that allows liquid water to exist even at temperatures far below the freezing point on Earth. As water droplets collide with ice crystals, the clouds become electrically charged. This triggers lightning, and Jupiter's lightning, as Juno's instruments revealed, is not comparable to what we experience on Earth. Using Juno's microwave radiometer, An instrument originally designed to measure water and ammonia in the deep atmosphere, scientists found that some lightning on Jupiter may be 100 times more powerful than lightning on Earth. Possibly far more. One previous estimate suggested the possibility of discharges 1,000,000 times more energetic. Even setting aside the extremes, Juno detected an average of 3 lightning flashes per second during certain close passes. In a single flyby, the spacecraft recorded 206 separate electrical pulses. The reason the storms can build to such extremes has to do with the composition of Jupiter's atmosphere. On Earth, water vapor is lighter than the surrounding air, so it rises easily and storms can form with relatively modest energy. On Jupiter, the atmosphere is dominated by hydrogen and helium. Water vapor is actually heavier than the surrounding gas. This means storms need vastly more energy to rise. And when they finally do rise, all of that accumulated energy is released at once in violent updrafts that drive cloud towers more than 100 kilometers tall, 10 times the height of storm systems on Earth. These storms also produce something that sounds like it belongs in science fiction. Planetary scientists call them mushballs. The idea was proposed to explain a persistent mystery in Jupiter's atmosphere. Ammonia gas was consistently depleted at depths much greater than any known storm mechanism could explain. Ammonia was simply missing from places where it should have been. Something was pulling it down. What appears to be happening is this. During the most powerful storms, updrafts are so violent that they carry tiny ice particles more than 60 kilometers above the visible cloud layer. At those extreme altitudes, ammonia vapor acting like a natural antifreeze melts the ice into a slushy liquid. As the particles cycle upward and downward, they grow larger, accumulating more water and ammonia, until they become dense, ice-encrusted slush balls. Big enough and heavy enough to fall deep into the atmosphere far below where the storm started, carrying large concentrations of water and ammonia with them. These are the mushballs. And new research, built on Juno's data and published in 2025, confirmed that this process is almost certainly real. The radio signatures detected during specific storm events could not be explained by any other mechanism. The mushballs fall. The ammonia is hidden deep in the planet. And what we see from above is only the surface of something vastly more complex. As we go deeper into Jupiter's atmosphere, the pressure builds. And under extreme enough pressure, gas does something unexpected. It stops being a gas. At a depth of around 1,000 kilometers below the visible cloud layer, hydrogen gas completes a transition into a liquid state. Not because it has cooled down, the temperature at this depth is actually well over 1,000 degrees. But the pressure is so immense that it overcomes the thermal energy keeping the molecules apart. The hydrogen is compressed into a liquid regardless of how hot it is. This is the largest ocean in the solar system. An ocean of liquid hydrogen, roughly 20,000 kilometers deep, 2,000 times deeper than Earth's oceans. And as we descend further, something stranger still happens. Under millions of times the pressure found at Earth's surface, at temperatures of around 10,000 degrees, the liquid hydrogen undergoes another transformation. The electrons that are normally bound to hydrogen atoms break free and begin flowing through the liquid independently. The liquid hydrogen becomes electrically conductive. It begins to behave not like a gas, not like a normal liquid, but like a liquid metal. This is metallic hydrogen. And Juno's data suggests that this layer of liquid metallic hydrogen is almost certainly the source of Jupiter's magnetic field, one of the most intense in the solar system, more than 15 times more powerful than Earth's magnetic field in some regions, and in places more than 50 times as intense. Juno also discovered something that had never been seen before in a planetary context. Jupiter's magnetic field changes over time. Not quickly, but measurably. A phenomenon called secular variation, which scientists had long observed on Earth but had never confirmed on another planet. The changes appear to be driven by those deep atmospheric winds, which shear and stretch the magnetic field lines as they move. One region in particular, at Jupiter's equator, concentrates much of this change. Scientists call it the Great Blue Spot, invisible to the eye, detectable only through magnetometer readings. It is a localized patch of intense magnetic flux, drifting slowly eastward, pushed by the winds. At its current rate, it would circumnavigate the entire planet in approximately 350 years, and then we reach the core. Or rather, we reach the region where the core is supposed to be. Before Juno arrived, the scientific consensus was straightforward. At the center of Jupiter, there should be a compact, dense ball of rock and metal. The same basic structure as the Earth's inner core, just scaled up. Maybe 10 times the mass of Earth, maybe a bit more. It would be clearly defined. It would have a sharp boundary separating it from the metallic hydrogen above. That was the model. Juno's gravity measurements said otherwise. By measuring tiny variations in the planet's gravitational field with extraordinary precision, tracking how these variations affected the spacecraft's radio signals back to Earth, Juno revealed that the internal density distribution of Jupiter does not match a compact core surrounded by a clean envelope. Instead, the data suggests something far stranger. The core of Jupiter appears to be large, much larger than expected, and it does not have a sharp boundary. It blends, gradually and continuously, into the surrounding layers of metallic hydrogen above it. There is no clear line where the core ends and the rest of the planet begins. Scientists describe it as a fuzzy core, or a dilute core. The terminology varies, but the meaning is the same. This is not a compact ball of rock and metal at the center. It is a vast, diffuse region where heavy elements rock, ice, metal are mixed in with enormous quantities of hydrogen and helium, in gradually decreasing concentrations moving outward from the center. By some estimates, this dilute core region may extend outward to encompass somewhere around a third of Jupiter's total radius. In mass terms, the heavy elements dissolved within it may be equivalent to more than 100 times the mass of Earth, spread across a volume so large that the mixture itself is the dominant feature of the planet's interior. The textbook image of a Jupiter with a solid center gone. What the data describes instead is something more like a gradient, a slow, gradual transition from a region richer in heavy elements toward one that is almost entirely hydrogen. No distinct layers. No clear boundaries, just a continuous shift in composition from the inside out. Here is what makes this so significant. It means that our understanding of how Jupiter formed, and by extension, how planets like Jupiter form anywhere in the universe, needs to be revised. The standard model of giant planet formation, called core accretion, begins with a solid core of rock and metal assembling in the early solar system. Once that core grows large enough, its gravity begins pulling in surrounding gas, hydrogen, and helium rapidly and violently, until it becomes a gas giant. Under this model, the solid core should still be there, preserved at the center, distinct and compact. But Juno's data suggests the core is not compact. It is diffuse, extended, mixed in with the very gas that was supposed to surround it cleanly. How did that happen? Scientists have proposed several possible explanations for how Jupiter ended up with a dilute core. The first explanation is the most gradual. During the formation of Jupiter, incoming solid material rocks, ice, planetary debris would have dissolved and mixed with the gas being pulled in. Over time, this mixing process could have distributed heavy elements throughout a large central region, creating composition gradients rather than a sharp core. The problem with this explanation, at least in the case of Jupiter, is that once the planet began rapidly accreting gas, the mixing process would have been overwhelmed. The flood of hydrogen and helium coming in would have diluted any gradients that had formed. Computer simulations of Jupiter's formation and long-term evolution suggest that even in the most favorable scenarios, the dilute region produced this way would be much smaller than what Juno's data implies. The second explanation invokes something more violent: a giant impact. The idea is that early in the solar system's history, a large rocky planet, perhaps 10 times the mass of Earth, collided with the young Jupiter with enough force to disrupt the solid core and scatter its material throughout a large portion of the interior. This theory was seriously considered for several years. It explained the extended dilute region. It had a certain physical logic. Then, in August 2025, a team of researchers at Durham University, working in collaboration with scientists from NASA, SETI, and the University of Oslo, ran a new set of high-resolution simulations of just such an impact. They used state-of-the-art software on the Dirac Cosma supercomputer. They tested multiple scenarios, varying the size of the impacting body, the angle of collision, and the conditions of Jupiter's interior at the time. None of the simulations produced a stable dilute core. In every case, the heavy materials disrupted by the impact quickly settled back down. The dense rock and ice, after mixing into the surrounding layers during the initial chaos of the collision, sank again under gravity, forming a core with a sharp boundary, exactly the opposite of what Juno observed. The impact shook the planet, as the lead researcher put it, but not in a way that explained the interior Jupiter has today. Which leaves a third possibility, and the one that is currently gaining the most scientific traction. The dilute core formed gradually, not through a single violent event, but through the slow, continuous process of Jupiter accumulating both heavy and light materials over millions of years as it grew. Composition gradients are, according to updated formation models, a natural outcome of the way giant planets build themselves with heavy elements distributed throughout the deep interior, their concentration decreasing outward with no sharp boundaries required. The gradients that formed early in Jupiter's history may have been preserved by a kind of stable stratification in the interior, where regions of different compositions suppress large-scale mixing over billions of years. The evidence supporting this gradual formation theory grows stronger for one particular reason. Saturn also appears to have a dilute core. Juno did not visit Saturn, but the Cassini spacecraft, which orbited Saturn for 13 years before being deliberately plunged into its atmosphere in 2017, gathered gravity data of its own. And researchers studying that data, along with seismic measurements derived from Saturn's rings, found evidence of the same kind of fuzzy interior, a large region of mixed composition, no clear boundary, heavy elements dissolved throughout. If two planets, very different in mass and internal temperature and detailed history, both ended up with dilute cores, it becomes difficult to argue that some rare and specific event, a single catastrophic impact, was responsible in each case. The more natural conclusion is that dilute cores are not a peculiarity. They are simply what the insides of giant planets look like. This conclusion, if it holds, has consequences that extend far beyond our solar system. Astronomers have now identified thousands of planets orbiting other stars, many of them comparable in size to Jupiter and Saturn. For years, scientists assumed that these worlds had the same basic structure assumed for our own gas giants, a compact heavy element core surrounded by a hydrogen and helium envelope, cleanly layered. That assumption shaped how we modeled their atmospheres, their evolution, their expected compositions. If Jupiter's interior is more complex than that, if it is gradients all the way down, no clean layers, no compact core, then the models for those distant worlds may need rethinking as well. What we see in their atmospheres may not represent what is inside them. The atmospheric chemistry of a gas giant, as new research on Jupiter suggests, is not necessarily a reliable guide to its bulk composition. Storms like the ones that create mushballs can unmix what was thought to be a well-mixed atmosphere, hiding material deep below the visible cloud layer and making the surface appear different from the interior. What looks uniform from the outside may be deeply, invisibly complex within. Most spacecraft that visited Jupiter before Juno flew along a path more or less level with the planet's equator. which means that, despite centuries of observation, no one had ever seen Jupiter's poles from up close. Juno changed that. Flying over the North and South poles on every orbit, it saw something that no model had predicted. At the North Pole, Juno found a central cyclone surrounded by 8 more, arranged in a ring around it, as though the 8 outer storms were bowing toward the one in the center. Each of these cyclones stretches more than 2,500 miles across. Their spiral arms press against each other as they spin. But despite the crowding, despite the immense energy of each system, they do not merge. They hold their positions, individually distinct, in a configuration that appears to be stable. At the South Pole, a similar pattern, 6 cyclones arranged around a central 7th. Juno observed this configuration, thought it had been mapped. Then, on a subsequent pass, a new cyclone appeared. A 7th outer storm had somehow developed and joined the pattern. Scientists are still working to understand how these polar configurations maintain their stability. Why do the storms not merge? What keeps them organized in these geometric arrangements? The physics is not yet clear. These are not questions that existed before Juno. They are questions Juno created. Juno completed its primary mission by mid-2021, but the spacecraft was still healthy, still transmitting, still seeing things worth seeing. NASA extended the mission, then extended it again. The final scheduled end of the mission is September 2025, at which point Jupiter's gravity will pull the spacecraft in and it will be consumed in the atmosphere. In the extended mission, Juno's evolving orbit brought it close enough to visit 3 of Jupiter's 4 large moons, the Galilean moons, the same 4 Galileo first identified in 1610. In June 2021, Juno flew within 652 miles of Ganymede, Jupiter's largest moon, the largest moon in the entire solar system. It was the closest any spacecraft had come to Ganymede since Galileo flew by in May of 2000s. The flyby altered Juno's orbit, shrinking it from 53 days to 43 and setting up a chain of subsequent encounters. In September 2022, Juno flew past Europa. Europa is a world covered in a shell of ice above a liquid saltwater ocean. The evidence that liquid water exists beneath that ice has been building for decades. Juno's microwave radiometer measured the thickness and structure of the ice shell in more detail than any previous instrument had managed. What lies beneath that ice remains one of the most compelling open questions in planetary science. In December 2023 and February 2024, Juno made its closest passes of Io, the innermost of the Galilean moons and the most volcanically active body in the solar system. The images returned showed what appeared to be fresh lava fields in areas previously mapped by earlier spacecraft. Io is alive with geological activity in a way that has no parallel anywhere else we have looked. These moons were not the primary mission. They were, in a sense, what the longer orbits made possible bonus science, as the mission team described it. Discoveries that were not planned for, revealed by a spacecraft that outlasted its original schedule by years. Scott Bolton, Juno's principal investigator, once described Jupiter as the Rosetta Stone of the solar system. The idea being that if you could read Jupiter, if you could truly understand what it is made of and how it got that way, you would have a key to understanding how everything else in the solar system formed. After nearly a decade of data, that key is still being cut. The fuzzy core is real, and its existence demands a new understanding of how Jupiter formed. But no one can yet say with confidence which formation path produced it. The gradual accretion theory is the leading candidate, but it is not proven. The composition gradients that the data implies are still incompletely mapped. The temperature profile deep inside the planet, which affects how those gradients are interpreted, remains uncertain. Even the total mass of heavy elements dissolved throughout the interior depends on which physical models you use to interpret the gravity data, and those models still disagree. The deep atmospheric winds that extend 1,900 miles below the cloud tops were confirmed. But what drives their structure, and exactly how they interact with the magnetic field and the interior is still being studied. The polar cyclones remain stable in configurations that theory does not fully explain. The Great Blue Spot continues its slow eastward drift, driven by winds at the surface, shearing magnetic field lines that no one could have detected without Juno's magnetometer. The mushballs may be real, the data strongly suggests they are, but the full extent to which they shape the atmosphere and what their presence implies for the interior composition is still being worked out. And beneath the ice of Europa, in an ocean that may have existed for billions of years, there is a question that Juno began to address and that future missions will inherit. The Europa Clipper, launched in October 2024, is scheduled to reach Jupiter in April 2030. The European Space Agency's JUICE mission, launched in April 2023, is scheduled to arrive at Jupiter in 2031. Both will study the moons in far greater detail. Both were informed, in their design and their science priorities, by what Juno discovered. There is a strange thing about Jupiter. For all that it dominates the solar system, heavier than every other planet combined, large enough to contain 1,000 Earths, it remains, in crucial ways, illegible. We cannot see its interior. We cannot drill into it. We cannot directly sample what is at its center. We have to infer everything from the outside, using gravity measurements and radio waves and the faint distortions that the planet's mass creates in the space around it. What Juno taught us, more than anything, is that the inferences we had been making for 400 years were incomplete. The model was not wrong because it was careless. It was wrong because the data to correct it simply did not exist. Galileo looked at 4 points of light and understood, after a week, that they were moons. That was the limit of what was possible in 1610. The limit kept moving. Pioneer, Voyager, Galileo, the spacecraft, and now Juno, flying lower over Jupiter's clouds than any mission before it, peering through the storms to find that the interior is not layered and clean, but diffuse and blended and strange in ways that still resist easy explanation. The core is not where we thought it was, or rather, it is everywhere and nowhere at once, dissolved into the planet itself, indistinguishable from the layers above it, extending outward until it simply isn't there anymore. We launched the spacecraft, we made the measurements, we received the signal, and when we looked at what the numbers were telling us, the planet turned out to be something other than the thing we had been picturing in our minds for centuries. That is the thing about science. The older the question, the more weight it carries, and the stranger the answer tends to be. Jupiter has been in our sky since before there were eyes to see it, and we are only now beginning to understand what it actually is. There is a storm on Jupiter that has been running continuously since at least the 17th century. We call it the Great Red Spot. It is the most iconic storm in the solar system. Astronomers have been watching it for centuries, sketching it, photographing it, modeling it. And for most of that time, what we understood about it was essentially this: it was big, it was red, and it was spinning. Juno told us how deep it goes. The answer was 200 miles, 320 kilometers, straight down into the ammonia clouds below. To put that in terms that feel real, Earth's oceans are, at their deepest point, roughly 7 miles deep. The Great Red Spot extends 50 to 100 times deeper than that. It is not a surface feature, it is a column of rotating atmosphere that punches down through layer after layer of Jupiter's interior, anchored by forces we are still working to understand. And it is shrinking. In 1979, when Voyager flew past, the Great Red Spot was approximately twice the diameter of Earth. By the time Juno arrived in orbit, it had contracted to roughly 1.3 times Earth's width. That is still an enormous storm by any measure. But the trend is real, and it is measurable. Something about the conditions maintaining the storm, the atmospheric dynamics, the energy input, the surrounding jet streams, has been slowly changing. No one knows whether the shrinkage will continue. No one knows whether the storm will eventually dissipate, or whether it will stabilize at some smaller scale and continue for another few centuries. The physics of what keeps a storm like this alive for so long and what might eventually bring it to an end is genuinely open. The red color itself is another layer of the mystery. The storm's cloud tops are higher than any other clouds on Jupiter, elevated above the surrounding atmosphere, absorbing more ultraviolet light from the sunday. That extra ultraviolet exposure drives chemical reactions in the storm's compounds, and those reactions produce the deep reddish-brown pigment. In a sense, the storm is colored by sunlight. The more it rises, the redder it gets. Think about that for a moment. A storm 200 miles deep, colored red by the sun, that has been turning continuously since before the American Revolution. That has outlasted every government, every empire, every civilization that has existed since people first looked up and noticed it in the sky. And Juno, flying lower over it than any spacecraft in history, showed us for the first time how far down it actually goes. 200 miles is the answer. But the question of why it persists, that remains exactly where it was. Before Juno could study anything about Jupiter, it first had to survive the journey toward it. Jupiter's magnetic field is the most powerful of any planet in the solar system. It is 15 times stronger than Earth's, and in some localized regions, more than 50 times as intense. That field rotates with the planet, sweeping through space like an enormous invisible arm, accelerating charged particles, electrons, protons, heavier ions to extraordinary energies. The result is a radiation environment around Jupiter that would destroy ordinary electronics in minutes. The engineers who built Juno understood this. They designed the spacecraft with a first-of-its-kind electronics vault, a titanium enclosure at the spacecraft's core, roughly the size of a car's trunk, weighing around 400 pounds. Inside it, protected from the particle barrage, were Juno's most sensitive instruments and computers. The vault was built to absorb the punishment of the radiation belts, while the science hardware inside continued to function. Even with that protection, the mission design accounted for the radiation by routing Juno on a specific orbital path, approaching Jupiter from the north, diving between the planet and the inner radiation belts, then exiting over the South Pole and swinging far out into space before the next approach. The closest point of each pass brought the spacecraft to within about 2,200 miles of the cloud tops. That sounds like a generous altitude. But if you scaled Jupiter down to the size of a basketball, that 2,200 miles would correspond to less than a quarter of an inch above the surface. Now, the magnetosphere itself. Scientists knew Jupiter had a powerful magnetic field before Juno arrived. Pioneer and Voyager had measured it from a distance decades earlier. What Juno revealed was that it is far more intense than those earlier measurements had suggested in some places, more than 30 times as powerful as Earth's equivalent field. And it is not smooth or uniform. The field has lumps, irregularities, concentrations that appear in unexpected locations and at unexpected strengths. This lumpiness matters because it tells us something about what is generating the field. On Earth, the magnetic field is produced by the movement of molten iron in the outer core, a relatively deep, compact dynamo. Juno's measurements suggest that Jupiter's field is generated at a much shallower depth than previous models predicted, within the layer of liquid metallic hydrogen rather than deep in whatever lies at the center. And because the metallic hydrogen layer extends through a large volume of the planet, the resulting field has a more complex, multi-lobed structure than a simple dipole. The auroras at Jupiter's poles, generated by charged particles funneling into the atmosphere along the magnetic field lines, are far more powerful than anything on Earth. The most energetic particles involved reach 400,000 electron volts. Earth's most powerful auroral events max out at a few thousand. These are not the quiet, shimmering curtains of light familiar from photographs of the northern lights. They are violent, continuous electrical events driven by processes fundamentally different from those that produce terrestrial auroras. The magnetosphere itself, the vast region of space dominated by Jupiter's magnetic influence, stretches so far that on the side facing away from the Sun, it extends outward as far as the orbit of Saturn. If it were visible to the naked eye from Earth, it would appear several times larger than the full moon in our sky. It is one of the largest structures in the solar system, and we had barely begun to understand it before Juno arrived. In December 1995, NASA's Galileo spacecraft released an atmospheric probe into Jupiter's cloud layers. The probe transmitted data for about an hour before the pressure and heat destroyed it. What it found was puzzling. The atmosphere at the entry point was strangely dry. The water content was only about 1/10 of what scientists had predicted based on their models of how Jupiter should be composed. This was a significant discrepancy. Water is expected to be one of the most abundant molecules in a gas giant's atmosphere. Finding so little of it suggested either that the models were wrong or that something unusual was happening at the specific location where the probe entered. That question sat unanswered for over 2 decades. Juno solved it. The Galileo probe had entered in the wrong place. Not through any mistake in planning, the entry location was chosen carefully. But it happened to descend into a region that scientists came to understand, with Juno's help, is anomalously dry. Jupiter's atmosphere does not distribute water uniformly. Near the equator, and in deeper regions of the atmosphere, water is far more abundant than the Galileo probe's entry point suggested. The probe had sampled a dry pocket in an otherwise water-rich world. This matters more than it might seem. The amount of water in Jupiter's atmosphere is directly connected to theories about how the solar system formed. Water, or more precisely, oxygen carried in water molecules, is one of the traces scientists use to understand the composition of the protoplanetary disk from which all the planets assembled. If Jupiter captured its material from the disk in the way the models predict, the abundance of water should reflect the conditions in the early solar system at the location and time where Jupiter grew. The Galileo probe's dry result had created a genuine tension with those models. Juno showed the tension was an artifact of a bad sampling location, not a flaw in the models themselves. But here is the deeper issue. If the distribution of water in Jupiter's atmosphere is this uneven, if a single probe entering in the wrong location could give such a wildly misleading result, then reading a planet's composition from a limited sample of its atmosphere is far harder than anyone had assumed. And if it is that hard for Jupiter, which we can study in extraordinary detail with a dedicated orbiter, what does it mean for the thousands of exoplanets whose atmospheres we are trying to read with a telescope from light years away? The top of the atmosphere is a poor representative of what is inside the planet. That single sentence, drawn from the work of researchers analyzing Juno's data, may be one of the most consequential findings of the mission. Not for what it says about Jupiter specifically, but for what it implies about every gas giant we will ever try to understand. Juno did not arrive in an empty sky. It arrived at the end of a long chain of predecessors. Pioneer 10 and Pioneer 11 flew past Jupiter in the early 1970s, the first spacecraft ever to visit the outer solar system. They confirmed that Jupiter's radiation environment was survivable just barely and returned the first close-up images of the planet. Then Voyager 1 and Voyager 2 arrived in 1979, and the world saw Jupiter as something truly alien for the first time. The chaotic cloud bands, the Great Red Spot in close detail, the volcanoes erupting on Io. The Galileo spacecraft orbited from 1995 to 2003, dropping a probe into the atmosphere, discovering evidence of a possible ocean under Europa's ice, and mapping the moons with unprecedented precision. Each mission asked new questions. Each mission left some of those questions unanswered for the next one. Juno is doing the same. The questions it has open the fuzzy core, the origin of the polar cyclones, the full structure of the deep atmosphere, the implications for formation theory. These are questions the next generation of missions will inherit. NASA's Europa Clipper, Launched in October 2024 and scheduled to enter orbit around Jupiter in April 2030, will study Europa's ice shell and subsurface ocean in far greater detail than Juno could, flying dozens of close passes and mapping the Moon with instruments that Juno does not carry. The European Space Agency's JUICE mission, launched in April 2023 and scheduled to arrive in 2031, will study Ganymede, Callisto, and Europa, eventually entering orbit around Ganymede in what will be the first time any spacecraft has orbited a moon other than our own. Both missions were shaped by Juno. The radiation environment measurements Juno gathered around the Galilean moons directly informed the designs of instruments on both Europa, Clipper, and JUICE. The data Juno collected on the structure of Europa's ice shell told mission planners what the Clipper needs to look for and how deeply it needs to look. Science builds on science. Each mission hands something forward. Juno itself carried a piece of that inheritance onward. Aboard the spacecraft, the Italian Space Agency provided a small aluminum plaque. On it, a self-portrait of Galileo Galilei, and a passage copied from his journal in his own handwriting. The January 1610 entry in which he first described the 4 points of light near Jupiter that would eventually bear his name. The spacecraft that was designed to see what Galileo could not carried his words with it into orbit around the world, he had first turned a telescope toward more than 400 years earlier. There is something in that detail that resists being explained away. Galileo wrote that around Jupiter there are moving stars, invisible till this time to everyone. He was right that they were invisible until that time. What he could not have imagined was how long the invisibility would last and how many layers of it there were still to peel back. The moons took a week to confirm. The atmosphere took 3 more centuries to begin reading. The interior, the actual interior, what the planet is truly made of and how it came to be, that is what Juno finally began to see. And even now, even with the most accurate gravity measurements ever taken of another planet, even with 9 years of continuous orbital data and instruments designed with a precision that would have been unimaginable to any previous generation, we are still at the beginning of that particular understanding. The fuzzy core does not have a sharp boundary. The science does not either. What we know about Jupiter today is more than what any previous generation knew, and it is almost certainly less than what the next generation will know. That gap between what we have learned and what is still there to be learned is not a failure. It is the shape of every real question worth asking. Jupiter is still out there, still turning, still holding most of what it knows behind clouds that no instrument has yet fully seen through. The great red spot still spinning, the polar cyclones still holding their formation, the fuzzy core still blending, imperceptibly, into the liquid metal above it, the way a secret blends into the person who keeps it present everywhere, visible nowhere, waiting for someone to build something precise enough to finally read it clearly. We are building it.